Hello, welcome to the next installment of Fluid Statics. In this video, we're going to work two more example problems, which should pretty much complete the content of the meeting or lecture. This first example is very simple, actually, although it's quite tedious. Not particularly a practical case, but it's a good homework or exam problem, and it will illustrate the principles of Pascal's law and manometers and changing fluids and moving up and down in a fluid using the hydrostatic pressure versus depth equation. I even have the calculator out because I'm going to check my work as I go, or I'm going to need it. Let's see if I can organize this a little bit more viewable. That's going to have to do. Okay, so here's our problem. We have water flowing through pipes A and B, so imagine that the water is flowing towards us in A and B, so it's coming out of the paper. And then there's this manometer that's comprised of oil and mercury. Oil has a specific gravity of 0.8 that's given to us in the problem statement. I'll color in the oil part in red. So here's the part that has oil in it. And mercury with specific gravity of 13.6 is in this leg, and then elsewhere is water. And it's good old yummy blue water, so I'll color it in blue. And obviously, practicing my coloring reminds me of my childhood. Okay, so there's our system. Water, mercury, oil, mercury, water. The various offsets of either the interfaces are shown on the dimension drawings, and we want to find the difference in pressure between A and B, and we're told to do it in units of pounds force per inches squared, which is a pretty unusual pressure unit. Usually it would be pounds per square inch, which would be, oh, that is pounds per square inch, I can't think. Okay, so the sketch and the problem statement are done for us. So let's just follow our procedure and we'll list the known values. So we know that the pipe contains water. And its specific weight is 9,800 newtons per meter cubed, same as 62.4 pounds per foot cubed. We'll do it in U.S. customary units. This is one of the few problems that I haven't converted myself to SI, so bear with me for our German students who are pretty much SI only and don't have to deal with this goofy U.S. customary system. The manometer fluids are oil and mercury. The oil has a specific gravity of 0.8. Mercury has a specific gravity of 13.6. We'll be able to use those to adjust behavior of the specific weights as we go on. What's unknown is the pressure difference, delta P, which equals pressure A minus pressure B. What governing equations do we have? We essentially have the variation in pressure with depth for a hydrostatic fluid equation. I believe in our textbook it's 3.21. We're going to take advantage of a slightly different formulation, which says that P2 is equal to P1 plus the sum of all the gamma i's, HI's moving down, minus the sum gamma i's, HI's moving up. And you'll need to read around that section to get a feel for what it is. What this is doing is it's just compactly expressing move from one fluid to the next, move from one fluid to the next, and so forth into a single expression. It's not necessarily terribly useful in this fashion, but it does give us the ability to state and remind ourselves what the governing equation is. And finally, we will begin the solution, which is essentially apply 3.21 from A to B. So there's our setup. Okay, so I'm going to make some declarations. I'm going to declare this as z equals 0. Okay, so I'm just picking a datum. That would mean that this location is z equals minus 10 inches. This would have to be z equals minus 7 because we moved 3 inches up. This one is going to be z equals minus 3. If we were minus 7 and we take 4 off, this becomes z equals minus 11. Minus 11 plus 5, z equals minus 6. And finally, here we have z equals plus 2. So now we have the elevations listed of all the particular points of interest. And let's go ahead and take advantage of that now. So we're going to go from A, and let's label these intermediate ones. So we have A, B, I'll call this one C, I'll call this point D, this one E, and that one F. So we have A, B, C, which is easy as 1, 2, 3, and D, E, F, which is 4, 5, 6. Sorry, Jackson 5. So we have the pressure at A minus the pressure at C, essentially using this formula, is equal to minus gamma water times ZA minus ZC. So all we've done is determine the pressure change to this point. The pressure at C minus the pressure at D is equal to minus gamma mercury ZC minus ZD. Later on we'll go ahead and put numbers in. We've now figured out the pressure to that case. If we were to move straight across, it's the same pressure here, so we're going to just drop those 4 inches. Pressure at D minus the pressure at E equals minus gamma oil ZD minus ZE. Then from E to F, we're now going to move up in that fluid. Pressure E minus the pressure at F equals minus gamma mercury ZE minus ZF. You'll notice I didn't mess with the sign. It's actually all going to be handled by these elevations. Finally, the pressure at F minus the pressure at B equals minus gamma water ZF minus ZB. Now we're going to these are all delta P's. We're just going to add them together and see what's left. So if I do that, I have the following. PA minus PC plus PC minus PD plus PD minus PE plus PE minus PF plus PF minus PB equals, well, let's see what we can cancel. There's a plus PC and a minus PC. They vanish. There's a minus PD and a plus PD. They vanish. There's a minus PE and a plus PE. They vanish. There's a minus PF and a plus PF. They vanish. So all that's left is PA minus PB. Okay, that was the left-hand side. We now can substitute in the right-hand side, so we have, well, let's call this delta P. This be easier to write. So now delta P is equal to minus gamma water, ZA minus ZB, minus gamma mercury, ZA minus ZC, ZC minus ZD, minus gamma oil, ZD minus ZE, minus gamma mercury again, ZE minus ZF, minus gamma water, ZF minus ZB. Now we can start to substitute numerical values in terms of inches or feet. I'll do it in inches because that's just extra confusing when we get to the end. So we have ZA minus ZB equals, ZC. I'm having troubles with my B's and C's. It's equal to 0 minus 10, so that equals 10. ZC minus ZD equals minus 10 minus 7, which equals minus 3. ZD minus ZE equals minus 7 minus 11, which is going to equal plus 4. ZE minus ZF equals minus 11 minus 6, which is minus 5. And lastly, ZF minus ZB equals minus 6 minus 2, which equals minus 8. And these are all in inches. Let's next figure out what we'll go ahead and just put these in. Now we have minus gamma W times 10 minus gamma mercury times minus 3 minus gamma oil times a plus 4 minus gamma mercury again times a minus 5 minus gamma water times a minus 8. So we can either figure out oils and mercuries or just convert everything into gamma water. So let's going to do that latter one. So that's minus gamma water times 10 minus 13.6 gamma water times a minus 3. So we've just converted mercury into an equivalent density of water, a specific weight of water, minus 0.8 gamma water times 4, minus 13.6 gamma water times a minus 5, minus gamma water times a minus 8 equals our delta P. All right, we know what the value, numerical value is of gamma water. So now all we'll have to do is factor out the water, the gamma water. So we have gamma water, which is a known value, minus 10 minus 13.6 times minus 3 minus 0.8 times 4 minus 13.6 times minus 5 minus 8. Okay, so these are going to be in this whole thing is going to be in inches when we get done. So now we use the gonculator. Let's do the intermediate calculations really quickly. So this is going to become gamma water times minus 10, 13.6 times 3, 40.8, 0.8 times 4, minus 3.2, 13.6 times 5, plus 68, minus 8. Now we'll do the arithmetic. So I have 40.8 plus 68. Found an error. That is plus 8. Now let's try that again. 40.8 minus 3.2 plus 60. This equals gamma water 103.6 inches. All right, so now we're ready to produce our results. So delta P is 62.4 pounds per cubic foot. That's our specific weight. There's 103.6 inches of net manometry change. 1 foot is 12 inches, so that's going to convert this whole term into feet. And 1 foot squared is 144 inches squared. That will convert the result into pounds per square inch, and I've already done the calculation ahead of time. 3.74 pounds per inches squared is the change. A brief discussion. I would go to a new page, but I don't necessarily want to use it. Okay, so we did direct use of static of so really all we did was direct application of static fluid and Pascal's law, and we used algebra and the specific gravity to reduce calculations. And you'll simply have to take it on faith or eventually convince yourself that in most cases the use of algebra ahead of time is a valuable exercise rather than banging through things in numbers, especially if we want to get to where we would script this into a programming tool.